Okay, everyone, good afternoon. Okay, my name is Yun Qi. I'm from the Department of Material Science and Engineering. Today is my greatest pleasure to introduce you Professor Peng Xuming from National Taiwan University, Taiwan. Well, that's me. He has spent over 40 years with the National Taiwan University. Well, I think he's a very good teacher, very good researcher, and he's also a very powerful so-called physical chemist. I think sometimes we call the political chemist. For example, he has been served as acting chair of the Institute of Chemistry, Academia Sinica, and he has been served as a departmental chairman of the National Taiwan University. And he also served as the vice president of the National Taiwan University, as well as the vice president of the Academia Sinica. Not to mention that he has been the president of the Taiwan Chemical Society, as well as the editor of the Journal of the Chinese Chemical Society. Okay, I think with that, he means he's not only very influential in Taiwan. In fact, he traveled to many countries in Asian area. Well, his research is focused on the coordination chemistry, particularly in the synthesis of the metal chain type of material. And he's also a very good crystallographer, and he helped Taiwan to build up the crystallography center, and then help many chemists in Taiwan to develop their career. I think in my case, I have to say I have collaborated with Professor Peng for over 30 years. And well, I think Professor Peng, he has been participating in publication in over 900 publications. I think that proves my previous point. He's a very good researcher. Well, today he's going to talk about his research, okay, titled From Mononuclear Metal String Complex to Heteronuclear Metal String Complex. Please join me to welcome Professor Peng Xuming.
Okay. Thank you, Professor Yun Ji, for your kind introduction. And it is my great honor and pleasure to give the IAS lecture today at the CTU. I did visit CTU probably 20 years ago when Liu Sutang, Professor Liu Sutang was here. But that time is the beginning of my research on this topic. But today, after 20 years, I think I have more to tell you. And I come from, I have my major appointment at National Taiwan University for 42 years. That means I came back on United States to Taiwan in 1976. I had my major appointment at NTU, but I also hold a giant appointment at the Academia Sinica. They also provide me a small space and 2 postdocs work on that site. They are celebrating 90th anniversary this year, okay? So National Taiwan University was founded in 1928 as one of the imperial university, but renamed as the NTU, National Taiwan University, after 1945. It is the most comprehensive university in Taiwan. And Academia Sinica, also founded in 1928 in Nanjing, but reactivated in Taiwan in 1954. So both of them are celebrating 90th anniversary. For example, I will fly back to Taipei tonight because tomorrow there's a tennis match for celebrating 90th anniversary. I have to play tennis tomorrow. Okay, and quite unique. Academia Sinica is also quite unique around the world because they consist of 3 divisions. They have the physical science division and life science division, and more had the literature, humanity, and social science division. So Academia Sinica is also quite unique among the academy of the world. Okay, anyway, today I'm really honored and pleasure to come to CityU. Okay, this is the outline of my talk. The first part will be homonuclear metal string complex. Some of them might not familiar with, but with the molecular model, you will see this is what I'm talking about. Beautiful metal string, okay? In the center, this model has 9 nickel, 1 by 1, and 4 ligand quadruply coordinate or wrap around this one. This is the metal string complex. Homonuclear metal string complex means all the atoms are same, okay? And this is the 9 nickel. Of course, this is even longer, 17 nickel. Okay? 17 nickel. Homo to hetero. Hetero means the metal string atoms are different. Okay. Then you can imagine the combination has so many. Okay. The problem is how to isolate the pure one single species and show their unique property. Okay, so this is first is homonuclear, the second is heteronuclear. The beginning is how we design new ligand and to form this unique metal string complex. The fundamental problem is the metal-metal bonding. So this research is to extend our cotton dinuclear metal-metal quadruple bond to trinuclear and even oligonuclear, okay? So we'll talk about metal-metal bond, and after it gets longer and longer, I claim this is a molecular metal wire because the modern analytical technique, so-called STM break junction, can connect the molecule to 2 gold gate and apply potential. When you current, you can get so-called IV curve of single molecule. From that, you can get the single molecule conductance. Of course, the conductance will depend on the type of the metal, also depend on the oxidation state. Then some kind of new generation from pyridyl amino to naphthylidyl amino and other things. The second part will be the heteronuclear. For example, even you trinuclear one, you can think about the type ABA, AAB, or ABC. Now we have more than 200 of this heteronuclear metal string complex. Okay, the other ones, at the end, I will give you a short conclusion. This field called molecular electronics. Maybe can we turn off the first half of the light, make the PowerPoint more visible? I don't need to make it. Okay, so this field called molecular electronics. Many on this cover you can see many of those molecules. Yeah, better. Many of these molecules are organic. Okay, conjugate organic molecule can be conduct current, and also asymmetrical organic molecule a donor acceptor type. Then when electron going through that will have the effect of rectifier. Or you can have the switch or memory. Today I will show you the complex we synthesize called metal string complex. And 2 years ago, molecular machine get recognition for Nobel Prize. Although molecular electronics is slightly different from molecular machine, but we are happy that the molecular chemists get the recognition. Again, for chemists, all the atom connect by chemical bond. Okay, the quantum mechanical approximation by linear combination of atomic orbital for organic people talking about sigma bond and pi bond. For low oxidation state of transition metal, using d orbital, you can see you have the sigma bond, the nodal surface overlap. You have pi bond, that one nodal surface overlap. Then unique for d orbital is the delta bond, that face-to-face d loop. Then you have two nodal surfaces overlap. That's why the name comes from delta bond. And for organometallic people, talking about metal-carbon bond. So this project began at 1994 when I applied that kind National Science Council. I just want to extend the dinuclear, localized dinuclear metal-metal bond to trinuclear or even to oligonuclear. So what new type of bonding, and then multinuclear metal-metal multiple bond. That my project 20 years ago. So if you want to do new chemistry with different from others, you have to design the new ligand. The ligand I designed is this oligopyridyl amino ligand. Oligopyridyl is a very good or important chelating group in coordination chemistry, okay? But in addition to the pyridyl, I got amine group in between. Of course, the synthesis is quite time-consuming. You have for longer one, you have the coupling reaction. But anyway, we can synthesize all the ligand. For example, n equal to 1, I name it a tripyridyl diamine, okay? So tripyridyl diamine also can act as the chelating ligand, like oligopyridyl. But under basic condition, you deprotonate that, the ligand can act as the bridging mode. So this is, you can see, our target molecule. The ligand actually are interested in themselves. They have cell recognition because pyridyl amino, by shift one base pair, you form perfect double helix, okay? I have a series of this structure, double helix. And in solution, with slightly acidic, in solution, acetonitrile, the ligand can chelating through form single helix. But today, I will talk about, under basic condition, we will form quadruple helix, okay? Quadruple helix. So this is the compound we will talk about today. For that 20 years or so, we synthesize trinuclear one, tetranuclear one, pentanuclear one. As long as we have the ligand, and we will use the Chinese, I joking, the Chinese cooking. I use male naphthalene as a solvent to fry the compound. And then I can get this series of compound. In this series of compound, the even odd number is more stable because symmetrical, odd number is symmetrical, and then metal string is well protected. But for the even number, it be unsymmetrical, you have isomer, and also more easily attacked by other nucleophiles to get the decomposition. In terms of metal-metal bonding, I just take the trinuclear as example, and for the 4D transition metal, the metal-metal bond is more notable. So first one, I'm talking about trileucinium with dipyridyl amide ligand. Okay, this leucinium is in 222 state, D6. And of course, this is the crystal structure. The bond length between leucinium is 2.25, short. Okay, according to the extended Huckel, or simplified molecular orbital, for the sigma bond, now you have linear 3 bond. So you have the all atom, all wave function in phase. This is bonding, and this one is non-bonding, almost no overlap, and this one is anti-bonding. because the wave function between two nuclei are in phase. That means your molecular orbital wave function will increase, and electron density will increase between two nuclei. That is bonding. For anti-bonding, you have out of phase. The wave function of molecular orbital decrease between two nuclei, and that indicates anti-bonding. For pi interaction, again, this is pi bonding has degenerate, and pi non-bonding, pi anti-bonding. And because of the helical structure, delta bond becomes very weak. So simple classification in this series, I have 3 bonding, 6 non-bonding, 3 anti-bonding, 18 electron populate up to pi sigma non-bonding. So we claim this is bond order of 3 because 3 bond pair in bonding orbital among this trileucinium. Of course, the actual ligand will play a very important role in the metal-metal bonding. When we move from chloral to cyanide, okay, the distance increased significantly from 2.25 to 2.37, okay? And magnetic property also change. This is diamagnetic compound. This is paramagnetic compound with 2 ampere electron. Okay, so simply molecular orbital saying this is a pi-based ligand. The pi orbital will low below, and it will interact this one and even higher the orbital. But this pi-AC ligand has empty pi star orbital, which will interact with pi star orbital, lowering the pi star orbital, then the sigma non-bonded, and you will populate 2 electrons on this pi star orbital, making the bond order from 3 to 2. That explains the bond length of lengthening of 2.37. Okay, move from lutetium to rhodium. D7 system. Now you have 21 electrons. So 3 electrons will populate pi star orbital, reduce the bond order from previous 3 to 1/2. 1/2 because bonding pair is 6, anti-bonding pair is 3. 6 minus 3 divided by 2. So that by the definition of bond order. So the bond length is 2.39. And we can further oxidize that, become cationic species. Then the bond length shorter because now the bond order is 2. So this bond length is very comparable to the previous dicyano trileucinium. Okay, so we make a good story about the trinuclear metal-metal bonding, and we just get the simple summary. For dinuclear metal-metal bonding, you have 1 sigma orbital bonding, 2 pi bonding, 1 delta bonding. So our Cartan discovered this metal-metal quadruple bond with 2.09 54 years ago. And you can see here is the bond order from 4 to 1 dinuclear metal-metal bonding. And here I already give you all the explanation about the electronic structure, the bond length, and also the magnetic property. But very interesting is that for the trinickel species, bond order is 0 because DA, you will populate all the bonding and anti-bonding. Bond order is 0. But synthetic point of view, the yield is highest one. So metal-metal bonding then contribute the stability of metal string. So this is the trinickel species. According to the previous analysis, I should take out these 2 sticks because the bond order is 0. But you know the OTAP diagram always show the distance is within the bonding, so they draw a bond. So what's the electronic structure of this 3 nickel? From structural analysis, terminal nickel has long nickel-nitrogen distance, showing its high spin, nickel 2. And inner nickel-nitrogen has short nickel nitrogen distance, 1.88, showing this is diamagnetic nickel 2. Okay, so spin state, there's no bond, 3 nickel 2 with the spin state 1, 0, 1. And this 1 and 1 show strong antiferromagnetic coupling. Okay, so antiferromagnetic coupling. And these 2 ampere electrons, one locate at the dd square, one locate at dx squared minus y squared. So the mechanism will be through different pathway. So this is the one pathway, this is another pathway, contribute the antiferromagnetic coupling. Okay, from 3 to 4, we synthesize dipyridyl diamido ligand. And we are certainly lucky enough, the student was lucky enough to isolate or get the crystal structure of the 2,2,6 isomer. Because as I mentioned, this is unsymmetrical. Quadrupole, you have many isomers. You have 4 heads on one direction, 3 heads on one direction, a tail, and 2 heads on one direction, and 2 heads on one direction have 2 sit position and 2 trans position. But they can get the crystal of this 2,2,6. Okay, the 2,2,6. And the structure showing that all the nickel has the short nickel nitrogen distance. That means all the nickel are diamagnetic, and whole complex is diamagnetic. Go to 5. We synthesize this ligand. Actually, when we start this project, this compound is simple, but nobody synthesized this before, and no literature report on this compound. We synthesize the new compound. Here is new ligand, and by the Chinese cooking, we use male naphthalene to form the pentanickel complex, and we can extract out and send the mass spectrum. It's very diagnostic because nickel has isotope, chlorine has isotope. This is the parent peak of this composition, and this is the experimental. This is a simulation one. It's like fingerprint, okay? Because you have so many isotopes, then you have the fingerprint. And when we simulate this one, I just jump up because it fits so well. Of course, we get the crystal structure of this pentanickel system, and inner nickel are low spin, outer nickel are high spin, and this is the crystal structure of that. Normally, I just get rid of the 3 carbon of the purity ring, become a dragon-like. So this 4 dragon, okay, wrap around this metal pillar, and this Taiwan dragon growing every year. In 2002, 2001, I synthesized 9 nickel, and now we synthesize 17 nickel. And again, there's a magnetic interaction now. Forget it. So the spin state is 1, 0, 0, 0, 1. So they are more far away, and the antiferromagnetic coupling becomes much weaker than the previous trinickel one. If we move the nickel to cobalt, from D8 to D7, now you have metal-metal bond. The cobalt complex has the distance here showing that it's shorter than the previous nickel distance, about 0.1 angstrom. So extended Hugo calculation showing that sigma bond, non-bonding, anti-bonding, and the rest all populate. So 35 electrons will populate up to sigma non-bonding. So whole complex only have 1 ampere electron, magnetic moment with 1.9, and 2 anti-bonding are empty. That means we have bond order of 2 among this pentacobalt moiety. So each cobalt has the bond order of half with sigma character. Okay, go to 9. This is the pentanickel system, non-nickel system, pentapyridiotetramine, and this is ball and stick model. Here, my colleague B.R. Jin, he had a very great interest in the bead work. The bead, 串珠, okay? So this complex is identical to that one, but with different presentation. The ball is atom, stick is chemical bond, showing the atomic arrangement in molecule. But the bead model here, that means each bead represents bond. So this is a bond model, okay? Each bead representing bond rather than atom in the molecule. So this two is identical. Here and here. But this is so-called bead model, each bead representing bond rather than atom. Okay? This is my favorite toy. In Cairo, and I just customize them. Okay? And another longer one is 17 nickel. This is my toy. You can play around. Okay, so Pendragon going from 1 nanometer to 2 nanometer, even to 4 nanometer, okay, 17 nickel. And some picture entertain you. This is the temple in Taipei. The dragon is not quadruple, but it. And this is in Shenyang Gugong, Dazhenting. You see the helical structure has the chirality. And these two dragons are in mirror image. Okay. 中文叫双龙抱柱. And this is a guest house near NTU. In the garden, they have quadruple brick pillar. I just took the picture with my molecule, quadruple one. And when I visited Japan, Scuba, they also had a very beautiful art piece with the quadruple one. As I mentioned, I will play tennis tomorrow. Okay, I play tennis, and I'm the great fan of Roger Federer. He's amazing. Okay, had ATP 99 champion now, hunting for his 100 championship. And in 2000 Miami, I just showed him. What I mean is the cup is also quarter pitch, quadruple cup. Okay. In Sydney, you have this one. They have octahedral, vertically connected and rotating. Actually, exactly the same as my that molecule. Please take a look. The inner sphere, the deep purple compound, is identical to this one. Each octahedral and vertically connect 9 of them and rotating the octahedral. Even in Moscow, they have quadruple sky tower. So it's quadruple, very interesting. Nowadays, we can attach the molecule to go gate, as I mentioned, experimentally, also can be theoretically, how you electron transport through the molecule. The right-hand side is the experimental IV curve for the chromium, cobalt, nickel. That means chromium is better conduct than the cobalt, than the nickel. Okay? Theoretical modeling show us that nickel and cobalt is quite consistent. Model show good consistent with experimental one. Chromium is not so consistent, but in the same order of magnitude anyway, because we only use actinic Huckel to treat the molecular orbital. It's not so satisfactory. But anyway, we get the theoretical model. Once you have the theoretical model, you can do local current analysis, see how electron goes through the metal string. And the answer is that 99% of the electron goes through the metal string. Only less than 1% goes through the ligand. This is already times some factor. So we really can claim that our metal string is the smallest electric wire. That means single atom wire, and again, like insulator in the bulk. So this is mimic microscopic copper wire down to the atomic scale. Okay, single atom and the quadruple ligand, it acts like an insulator, and we claim this is the smallest. Many people will ask what's the conductance, because the single molecular conductance is different from the bulk. You just the different scale, different thing. Here I show you our nickel, cobalt, chromium from 3 to 5 to 7. This is the value we get in mega ohm, okay, that the absolute value. Oh, because it's homolog, you can get the beta decay constant, okay, like here is 0.2. So I just want to mention to you that this value is quite comparable to organic wire. You can see those is organic conjugate wire. The value of resistance is about 100 mega ohm, same order as our metal spring, and the decay constant is also quite similar. So I only like to say, because this is a collaboration work with the Junxian Chen, many work, but I just say metal spring complex, their conductivity is comparable to organic. Many people start organic wire. Nowadays, we even can apply potential to the two tip. This is so-called STM break junction methodology. We can apply potential to two tip. That means we can tune or the Fermi level of the electrode. Okay, when you tune the Fermi level of electrode, the conductance will depend on the Fermi level. So before HOMO, you have one state. After HOMO, you have the reduced state. And near the HOMO, we get big turning current. For example, here is the electrochemical potential. When we scan, this is the so-called before oxidation. After oxidation, the current will be different. When the result happen, we have this resonant ternary and get big current. So we now can get like a spectrum. You can know where the HOMO of the metal spring are. Okay, back to chemistry. Second generation is naphthalidil group. When I was a graduate student, I already know the work. Naphthalidil group, because it's neutral and it's chelating, it will stabilize nickel 1, nickel 2 mixed valence compound. Okay, this is nickel 1, nickel 2 mixed valence compound. So I use tripyridyl diamine to bis naphthalidil and this will be less anionic because this has dianionic is less anionic. So using this ligand by Chinese cooking, similarly we can get the compound isoelectronically with previous tripyridyl diamidal, but now carry out 4+ charge, 4+. Okay, because this only one anion. Previous you have dianion, and this spin again is 1,0,0,0,1. But this can be easily reduced 2 electrons to get the nickel 1 in the center, not center, in the inner. And when you have nickel 1, very easily, because the last electron will go to dx squared minus y squared, which is the metal ligand antibonding. So you can see the metal nitrogen distance become longer. Okay, so we can do all the magnetic property. This antiferromagnetic center is more strongly coupling with another one, much stronger than the previous pentanickel system. And most important thing is that the conductance increased 40% by introducing this mixed valence unit. Okay, we think many things can be done because this mixed valence unit and this mixed valence unit electrochemical study they can study their communication and so forth. So going longer and longer. Yeah, this is another form. Some people I will show that another form of the helical type. This is the helical one, and I will show you the meso metastring later. Anyway, thank you. So we synthesize the tetranafthalidyl triamido ligand and get the complex. Because that's anionic. Those things are neutral. Those purely amino are neutral. Because every 2 nitrogen, you have 1 negative charge. Quadruple, you have 4 negative charge. So 2 plus of this metal string will cancel out the charge. So if you are keeping lengthening the metal string, the metal complex is still neutral. This is neutral one. This is neutral one. But for the non-static series, it's different. You accumulate charge. For this example, you will A plus. So it's very easy to reduce by 4 electrons at each naphthalidal unit. And we have the crystal structure of this 11 nickel. And the hook representing the naphthalidal unit. So it's symmetrical. So I only show you the 4 nickel. Okay. Once you have the nickel 1, nickel 2 mixed valence unit, the nickel nitrogen distance becomes longer. And nickel distance becomes shorter. So this is the bond model of this metal string. When you have mixed valence units, actually you have the partially sigma bond. And so recently, we even had the pyridyl naphthalidal unit hybridized ligand. And we can use the ATM, ultra low high vacuum, low temperature ATM to see the molecule. Because when you get longer and longer, the yield becomes lower and lower. It's very difficult to further purification or crystallization. So most simple way is you can see the molecule. This is a ultra high vacuum, low temperature ATM. We really think we have to see this molecule, this another 11 nickel molecule. And also many interesting property. The ligand can be hybridized between naphthalidal and pyridyl. So this one has the naphthalidine in one side, amido group in other side. So that means this side is more anionic, this side is more neutral, and because this phenyl group, we use stereochemical control, can get 4,0 isomer. That although it's unsymmetrical, but I can force this 4-phenyl group only on one side. So this unsymmetrical coordination geometry will stabilize. This one will stabilize nickel 1, nickel 2. This side, because more anionic, is stabilized nickel 3. So this is the one example possible candidate for rectifier. This is the nickel 1, nickel 2, nickel 3 coexist in one stream because coordination environment are different. And recently, we even use the anthracyclidine to get the nickel metal complex. And this anthracyclidine also had the mixed valence unit with 3 nickel, 5 plus. Very easy to reduce. L-stable nickel 1. So we also get all the electronic structure and interpretation. Another thing is the chiral control. As I mentioned, helically, they are chiral. They have left-handed and right-handed. Normally, you get racemic mixture. And this racemic mixture called crystalline is central space group that we are called racemic. Okay, but use this induced chiral. We attach this ligand by one camphor, the chiral complex. With camphor minus, we can get the delta form, with the camphor plus, we can get lambda form. That means you use the chirality of the camphor to control the chirality of the quadruple helix. No problem. Okay, so we can get a bottle of left-handed or right-handed quadruple helix. And this two form even hit to 100 degrees with few days, the CD spectrum remain, so they are not racemizing. Go to second part, heteronuclear metal string. Before that, or homonuclear metal string. You use nickel, you will get nickel metal string. You use cobalt, you will get cobalt metal string. But now we mix the metal. You can imagine that for the here has 7 metal in one position. So number of isomer will be the 7 to the power of 3. So many possible isomer. Okay? Like a pure metal become metal alloy, you have new chemistry and physics. Okay? So this is one micro review. We say like conceptually we have the vending machine, and you put the ligand coin in, choose the metal, come out with your homemade heteronuclear metal string. Okay. Of course, we have the strategy. I name it with thermodynamic control. That means which stable, or kinetic control by metal substitution. Or even in the worst case, you have so many compounds, some of them you can use column to separate the isomer, okay? And characterization, mass is also diagnostic, because many transition metal has isotope, or paramagnetic MMR, or single crystal now has faced the problem because you had the heteronuclear one. X-ray cannot differentiate nickel and cobalt because only differ by 1 electron in electron density. So in the same row, you have the difficult to characterize them by X-ray diffraction. But now we try to use neutron diffraction, okay? Because the nuclear cross-section for the nickel and cobalt are completely different. Okay, this is paramagnetic MMR. Cobalt, nickel, cobalt, we have the 8 peak, okay? It's 4 peak, the symmetrical one. For cobalt, nickel, we have 8 peak, okay? So MMR also very diagnostic for symmetrical or unsymmetrical because the number of the proton is different. The first one we get 10 years ago is cobalt, palladium, cobalt. I call it thermodynamic because you just mix the palladium 2 and cobalt 2 together. You can get about 30% yield of cobalt, palladium, cobalt. Because this 3 nitrogen has a different donating power. If you use the Pauling resonance concept, actually this amido carry out half of the negative charge. Pyridyl only carry out quarter of negative charge. So they are different. And the central one prefer the Da metal because the square planar if you neglect the metal metabolic. So this I call it the thermodynamic control because the middle one, they prefer Da metal. So, and this structure, cobalt, show anti-ferromagnetic coupling. From this point, so I can choose the nickel 2, copper 3, palladium 2, platinum 2 as the central one. And terminal, previous is D7. Now I can synthesize from D5 all the way to D10. Next one show you the D9, DA, D9 system, okay? And D9 only goes the anti-ferromagnetic coupling only through delta interaction because the only last electron was located in dx squared minus y squared. So this we can explain why the anti-ferromagnetic coupling become lower and lower. And this series we just published this year, we get compound iron 2, nickel 2, iron 2, and mixed valence iron 2, iron 3, and also oxidized species iron 3 and iron 3. Most interesting thing is that in the mixed valence unit, iron 2 and iron 3, different Da metal will mediate their interaction. When the central ion is nickel 2, the iron 2, iron 3 is delocalized from the Merz-Bauer spectrum. You cannot differentiate which one is iron 2, which one is iron 3. They are delocalized. But when you change from nickel 2 to palladium 2 or platinum 2, then this mixed valence becomes localized. Merz-Bauer show you that they have iron 2, iron 3, iron 2, iron 3. So the central ion can play important role to mediate the communication in the mixed valence one. Furthermore, we can use the third metal ion to substitute the terminal one, become ABC, okay, or ACB. And we study seriously, so the substitution sequence is that nickel can substitute cobalt, can substitute iron and manganese and cadmium and copper too. And in coordination chemistry, the very famous Irving-Williams series shows the stability, including thermodynamic stability of metal compound in this series. Okay, we are consistent in this way. But copper 2, actually, this is not copper 2. We substitute the metal in high temperature. Not only high temperature. So in that temperature, about more than 100 degrees, the copper 2 easily reduced to copper 1 and become labile. So this is, I can say, it's consistent with the Irving-Williams series. So now we can have many series of compounds: nickel, palladium, copper, cadmium, palladium, cobalt, many compounds. Another series is that dileucinium or diamoniminium. You will have the metal-metal bond. They are tied up together. So leave the third position. This is AAB, okay? For example, when we cook the leucinium and cobalt, we get the leucinium-cobalt trinuclear one. Very interesting, in this case, even ammonium can extract out the cobalt ion, become dinuclear one. And has 4 zero isomers. That means you have 4 pending pyridyl group. So it should be a very good chelating ligand. Chelating to coordinate, to keep the third ion in this position, from manganese to zinc, from leucinium to cadmium to elysium. So in this paper, we just the cover like metal clamp. You know, nowadays a lot of shopping mall has those door clamp. Okay, this is I call it metal clamp, can clamp all of the different metal ion. Another clamp is dirhodium. Dirhodium has a structure of 2-2 trans. 2-2 trans. Has 2 pyridyl on one side, another 2 pyridyl on the other side. But still, they can clamp, they can catch the third metal ion with rhodium metal, even this almost the same series. So this rhodium metal, of course, you can think the mechanism is that when they coordinate or catch one ion, the other 2 ligands will have the 1-2 shift to get the compound. Okay, so here is some compound, here is some many. Even that, the 2 can be silver, rhodium, silver. Okay, I think I'm running out of time. I have many trinuclear species. I just go to the final one, the pentanuclear series. Of course, it had much more possibility, but still we can get something out. When we mix nickel and lutetium together, we can get nickel, lutetium, nickel metal string. Lutetium located at 2-3 position. Although X-ray show nickel and lutetium is disorder, but no problem for the confirmation. When we cook with lutetium and cobalt together, we get lutetium, cobalt. Lutetium located at 1-2 position. Our easy explanation is that tricobalt is a stable unit with metal bond. Okay, that's our simple explanation, but still quite complicated. Anyway, what's the unique property of this metal string in terms of conductance? If you measure the single molecular conductance, this will pentalutetium is better conduct than the cobalt and nickel. But when you mix them, you get the between. But for the lutetium nickel metal string, this is the black line is the IV curve of the heteronuclear metal string. It shows very interesting negative differential resistance effect. That means you apply the potential, this will be dropped, then you increase again. Very interesting, if I put the IV curve of the lutetium and nickel together, you can see in some potential, this mixed metal string consists with lutetium. And in some potential, this mixed metal string consists with the nickel. So you can change the mixed metal string between two types. Okay? But of course, it's on different potential. And our explanation is that because the electric current electron through the molecular orbital, and some of the molecular orbital dominate by lutetium, it will lutetium light. If you dominate by nickel, it will nickel light. And when you apply the potential, as I'm showing, you are scanning the Fermi level. And the Fermi level reach some molecular orbital which dominate by lutetium. Then you get lutetium light. Okay, this is our explanation. When we submit the paper, the physics don't understand us and get a very critical comment and hard time for public. Our chemistry language is different from the physics. Anyway, this is very unique phenomenon. Finally, we published it anyway. And this is another form. I'm showing you the helical chirality. That when you learn organic chemistry, stereochemistry, if you have two chiral centers, you can have the mirror between them. That means you have meso carbon. In Chinese, it's called 内消旋. Racemic is 外消旋. Meso is 内消旋. And in the metal string is that in the upper half, I have one chirality. In the lower half, I change to under chirality. Then you will have the mirror between them. And this metal string, I call it the meso metal string. You have metal string, mirror in that, and not chiral at all. So, in this compound, monominum, nickel monominum, you can see the conformation. We not have the meso conformation or configuration. So this is the compound has the non-chiral, and our explanation is due to this quadruple bond. Alignment of this quadruple bond to give you more linear line. That means you will have the meso conformation. The last one, I will show you that we have the synthesis, the nickel, platinum, cobalt, palladium tetrametal string. Okay, as I mentioned, thermodynamically, this nitrogen prefer Da metal, but because the Da metal are inert, they are difficult to get two of them or substitute. So most easy way, even though for the penta-cobalt system, by our Chinese cooking, we can get 27%, not too bad, cobalt, platinum, cobalt. Okay, this is the first step stepwise, then you use the labor of palladium. Get this position, okay? And further, you use the nickel to kick out another terminal, cobalt. So get nickel, platinum, cobalt, palladium. All of them, although are fully characterized, but as I mentioned, they still have the question, how about this is nickel? Because from the X-ray, you cannot differentiate nickel and cobalt. You can differentiate platinum with other because they are third row. Palladium, second row. These are first row, okay? From the X-ray, even we have the mass, we have the symmetrical and unsymmetrical MMR, but still very hard to convince that we really get this compound. Okay. So only the most of the work I talk today are published. You can see the number, but only this one has not published yet. Okay, I think about the time, I'd like to give you conclusion. As I say, 20 years ago, I applied to my National Science Council to get metal-metal bond from dinuclear to trinuclear. The simplified dinuclear MO is that you have sigma bond, pi bond, delta star, pi star, sigma star. So build up, you get default configuration, you will have metal-metal quadruple bond. So Al Cartan found this quadruple bond with the equipped square planar upright 50 years ago, and he's really waiting for the Nobel Prize, but unfortunately he passed away in 2007. This is simplified 3-center one with our helical structure, 3 bonding, 6 non-bonding, 3 anti-bonding, as I show you on this part of the structure variation. We extend this trinuclear one to oligonuclear and really unique metal string complex, and claim as the molecular metal wire. We can measure their single molecular conductance, even simulation them. And we have the new generation to introduce the mixed valence unit to increase the conductance. And we also can have the chirality control with chiral control the chirality of this quadruple helix. Recently, we made many progress on this heteronuclear metal string like this one is nickel, cobalt, rhodium. This is maybe a few examples of cobalt, rhodium, sigma bond. This is diamagnetic, so it has to be cobalt, rhodium, sigma bond. And final goal is that this is our dream to get everybody our compound to do some research, for example, in catalyst or in other material. And again, this is a summary in Chinese. In one sentence, we synthesize world's thinnest metal wire and measure the conductance. And this is the student give me as the 60-year birthday gift as the puzzle. I never really put it. It's just in my office. This is the nickel metal string with nickel mixed valence unit. This is cobalt metal string with delocalized sigma bond. This chromium metal string with the quadruple bond, no bond, quadruple bond alternating. So you see different metal ion will have the different electronic structure. And thank for, I still didn't change them, this National Science Council, but it already changed to Ministry of Science and Technology, funding agency, and my NTU and Academia Sinica. Recently, I have the collaboration work with the BRG and Chen Junxian, who do theoretical study, and Chen Junxian even do I say the measure the conductance is really difficult work. Okay, so conductivity measurement, and only one or few slides for entertain you. This is the Taipei city, the 3 sides, the mountain, and this picture is taken on the east side, very unique. Taipei 101. It was the tallest building between 2004 to 2010, after Dubai Tower take the title. And in every year, they have the firework. in 2011, they claim to have the dragon, you know, I'm Pendragon. So I have the dragon fabric, and this is the theoretical value, and this is the experimental value. This is our campus. NTU is more comprehensive university. It's the Royal Palm Boulevard with 30-meter height and with the 40-meter wide. Royal Palm Boulevard. At the end is our main library. This is the chemistry research building with we can accommodate 40 research group. Now it's about 35. Okay, this is the chemistry research group. Even from there, we have the one irrigation canal that 250 years ago irrigated the Taipei plant, but we just restore or reactivate this small park in front of our chemistry building. Another view. Another view of my Chandrila. This is tetranafthalidyl triamidal. I make it in 2009, and I have the keychain of the Chandrila, and I give it to the chairman, and he really honored me at the Sun Factory to produce this for me. So every time I have the guests come to visit us, I very proudly show my molecule by shining the light, because normally the light will be off, although it's LED light, but the electricity will consume about the one air conditioner. So I turn it off, and one. Thank you for your attention.
In today's lecture, Professor Pen Xunmin, he just used a very simple design of a chelate. And to build up the complex, and I think the number of metal can be ranged from 3, 5, 7, all the way to 17.
17 is one pitch of the quadruple. One from here to here, one pitch. It's no limit, but I need manpower, and maybe very, very wasteful manpower, because the synthesis of the ligand is very hard. And
I do agree it's very difficult, okay, and I think, well, skill, or sometimes we should call it as an art, because, you also need to have luck to be able to isolate that kind of compound. And after that, they also change strategy, okay, I think they are switch to the mixed metal system. I think that even require more skill, because lots of different combination can take place. Okay, I think it's a very wonderful piece of research work. And now I think this lecture is open for discussion. Please.
yeah.
Thank you so much for your very interesting lecture, Professor Pen. So the synthesis for me is magic. So for the bimetals and the trimetals you show us, I'm just wondering. I remember one example is maybe 66% of one metal, and then the other is 33%.
Yeah.
And how do you really control? I think it's random, right?
Not random.
How to control the order of the metals, and then how to really purify those kind of trimetals or complex?
Yeah. Because the first is the ligand synthesis. Once you have the ligand synthesis, now for homonuclear one, the characterization almost no problem, because you only have one kind of metal, and you start from nickel, your metal string will be nickel metal string. You start from cobalt, your metal string will be cobalt. I think you are talking about the heteronuclear metal string. Of course, the heteronuclear metal string. It case by case. Some of that so-called 33%, 66%, that the crystallography disorder. Okay, like we have metal string, all the same shape. Okay, when you get the single crystal, the position, not position disorder, crystallography disorder, when they pack, okay, this one will pack cobalt, nickel, nickel, okay, and in other symmetry related one, maybe nickel, nickel, cobalt. So the cobalt and nickel, when you put together, is disorder. It's not positionally disorder in terms of molecule, but it's positionally disorder in crystallization. Okay, so 33rd or half is that, for example, in the pentaunion system, okay, I claim that I have the nickel, ruthenium, nickel, okay, but in the other metal string, maybe nickel, ruthenium, nickel. So crystallography say the 2 and 4 position, nickel and ruthenium, is disorder. But you take out in one molecule, it's not disorder. It's just nickel, ruthenium, nickel. Or you turn around, you come other way. So that's not positional disorder in molecular chemistry. It's crystallography disorder because the molecule looks same, packing is the same. So that percentage is the crystallography disorder. Of course, as I already say that you want to convince people that you have this series of position. It's difficult. Okay, they can challenge you with all the other possibilities. But from our experience, we know, I say we have strategy, thermodynamic control, and amino, nitrogen, preferred DA, metal, that's our experience. And we have the substitution series, which metal like substitute, which metal, and those accumulation of those experience will show us or tell us how to synthesize heteronickel metal string. It has so many different strategies. So I cannot really give you the short answer for you. Yeah, it's difficult. In each case, I have to explain and students work hard to get them. So there's the way. I just say there's the way, thermodynamic, kinetic, or even chromatography them. You know, organic mixture, you just chromatography them, you get every component. If they are stable and can be chromatography, you can get everything.
Any other question?
Yeah?
I saw there are some examples using copper and
Yeah?
metal plane to get silver atom.
Yeah.
I just want to ask, did you try using just getting the gold atom? I mean, using gold atom to synthesize.
Yeah.
So it's also okay to use gold atom?
Only gold atom? You mean homonuclear metal string with gold?
Homo or hetero?
Hetero is no problem. We have some, like silver ones, actually can be gold. Rhodium, gold. Gold one, no problem at all. You can see, as I mentioned, our metal string, this metal string, because the charge, they stabilize in the 2 states. Nickel 2, cobalt 2, ruthenium 2, and 2 states. Gold only have gold 1 or gold 3. Okay, so if you want to get pure gold chain, it will be difficult. Okay, so if you have the gold 1, use the phosphine. Then Jimmy Chi has the tri-gold with the phosphine ligand, but not in this series. This series are all more because it stabilizes or can accommodate metal in 2 states, 2 plus. Okay. So in gold chemistry, there's only no gold 2 state.
Thank you.
Thanks for your very comprehensive and systematic talk. So I noticed that throughout your presentation, you always choose the extended Hooker method as your computational method. So I try to understand why density function theory is not a good choice for metal-metal bond, and metallic system. Why extended Hooker could be a good choice to properly describe the electronic property of your systems? Thank you.
So as I already give a comment that the metal-metal bond is not the key factor for non-forming metal string. In our experience, you can see in my presentation in the first part, homonuclear one, the high yield or crystallized things is the nickel metal string, nickel 2. And I claim again, the nickel, there's no bond or bond order of 0, okay? But our experience or experiment shows that the nickel metal string is most easily formed. And the explanation is that nickel favor is labile. You say palladium, but palladium is inert. It's very difficult to get all the ligand out and our metal string nitrogen coordinate. So when you want to get the metal string, your metal ion had to be quite labile, okay? And again, labile Da configuration is nickel. That's my explanation. So the most easy synthesized metal string is nickel. And although there's no nickel-nickel bond, but in each nickel is square planar and can be squeezed by the ligand to get closer distance, about 2.25. So like this one, the nickel-nickel distance is 2.25. And in our experience, from nickel to cobalt, the yield will decrease about to 1/3. Even to the other metal, will even lower. Okay, so this is just our experience. No theoretical so-called reason for that. And so, what other question? Yeah? So that is the explanation of the nickel metal string. Most easily formed is nickel metal string. Okay?
Any other question from the audience? If not, I have the final one.
Okay.
I think you try to draw an analogy between your complex and the metal Y. However, your complex was produced by metal cation. I think all the ion were either the I think majority of them the 2+ cation. However, for the metallic conductor, they always at 0 oxidation state. So basically, I think these two kind of material were different in character. And can you make a comment on that?
Yeah, this is just more like general scientific sense. I'm not trying to differentiate the 2+ or nickel 2+ or nickel atom, because the thing, of course, the oxidation state. One way is to count how to count the electron. Okay, not really nickel 2+. Okay, so anyway, this one is neutral species, compensated by amide nitrogen. Okay, so you are right. In chemistry, we are all classify oxidation state very clearly. Okay, but that the way of the counting electron. Okay, this will be really between, the Linus Pauling. They have a neutral electron neutrality principle. In the stable complex, every atom has the charge less than 0.5. Okay, so yes, I'm not really differentiate that. This is just some kind of the analog claim to make them to understand what the chemistry I'm doing. I'm not really optimistic to really realize this in so-called molecular electronics, because any realization process had to be, compound will be cheap, and the synthesis will be simple, and the product should be stable. None of them fulfill my compound. None of them fulfill the condition because it's not stable in aqua. Many biological people like this metal spring has the same pitch as DNA, 35 angstrom. Maybe they can bind to DNA or something, but the compound is not stable in aqua. Long time, not stable in aqua because the amino nitrogen will be hydrolyzed. So biological application is limited by the stability in aqua. So I'm just you can say for curiosity or for fun doing my research. The application side not opportunistic at all.
Okay, I think I think we already used our time. Finally, I think I'd like to present a gift from the university.
Thank you. Okay.
Thank you.
谢谢，谢谢，谢谢。